There is a geologic gate in Southern California, and right now, the stress pushing on it is higher than at any point in the last 1,000 years. This is not a metaphor, it is a measurement. A team of geophysicists published the data on June 3, 2026. They called it the Cajon Pass Earthquake Gate, a junction where two of the most powerful fault lines in North America converge. A place that can either stop a catastrophic earthquake in its tracks or allow the rupture to jump from one fault to the other, unleashing a seismic event that models have only begun to comprehend. That gate is now loaded for failure. It is holding back a millennium of tectonic pressure, and scientists are warning that the lock is beginning to break. So the real question is, what happens when it finally swings open? California was never supposed to be stable. The state is built on a geological scar, an 800-mile wound in the Earth's crust called the San Andreas Fault, where the Pacific Plate grinds relentlessly northwest past the North American Plate at a speed of about 1 inch per year. Most of it runs through unpopulated deserts and remote mountain ranges, a problem for geologists, not for metropolises. That was the story, a story that was dangerously incomplete. The San Andreas Fault is famous. It is not, however, the state's most dangerous. That title belongs to the Hayward Fault, shorter, less powerful, and running directly beneath the homes of 8 million people. The Hayward Fault is a 74-mile branch of the San Andreas system that slices through the San Francisco East Bay, under Oakland, Berkeley, and Hayward. It threads beneath hospitals, schools, freeways, and the foundations of a stadium. It is, according to the U.S. Geological Survey, a tectonic time bomb. Its last major rupture was in 1868. Seismologists calculate its natural cycle of rupture to be roughly every 140 to 150 years. We are now well past that anniversary. The strain has been accumulating, quietly and without interruption, for over a century and a half. The fault is overdue, not by a little, by decades. A magnitude 7.0 earthquake on the Hayward Fault is not a question of if, it is a forecast, a mathematical probability closing in on certainty. For years, the models of that earthquake were already devastating. But the reality, as scientists discovered in the spring of 2026, is profoundly worse. Something had to be simulated, on a scale never before possible. Engineers at Lawrence Livermore National Laboratory had a single objective: build the most complex, high-fidelity 3D model of a Hayward Fault rupture ever attempted. A team led by seismologist Dr. Arbin Pitarka used the nation's most powerful exascale supercomputers to simulate not just the fault breaking, but how the seismic energy would travel through the specific, unique geology of the Bay Area. What they found changed the definition of a worst-case scenario. Older models treated the ground like a uniform solid. They were wrong. The East Bay is not solid. It is a collection of deep, soft, sedimentary basins, places like the Livermore Valley and San Pablo Bay. Think of them as geological bowls filled with soft soil and rock. When a seismic wave, kinetic energy from the rupturing fault, hits the edge of one of these basins, it does not just pass through. It gets trapped. Dr. Pitarka's simulations, published on March 17, 2026, proved it with terrifying clarity. The energy enters the basin and begins to slosh back and forth, reflecting off the hard bedrock walls of the valley like water in a bathtub. The shaking does not stop when the fault stops. It continues, resonating inside the basin, growing in amplitude. The ground keeps moving, longer and harder than anyone had previously modeled. By how much? By up to 50%. 50% more kinetic energy. 50% more time for buildings to fail, for bridges to buckle, for gas lines to sever. This is the basin trap effect. A known phenomenon that had never been visualized with this level of accuracy. It transforms a 45-second earthquake into a nightmare of rolling, amplified ground motion that can last for well over a minute. The very ground that 8 million people live on becomes an amplifier for its own destruction. It was a staggering discovery, a new layer of risk for a region already living on borrowed time. And yet, it was only the first warning. Because 400 miles to the south, on the main trunk of the San Andreas itself, an even stranger signal was just beginning to emerge. There is a town in central California called Parkfield. Population 18. It has a single cafe, a small bridge, and more military-grade seismometers per square foot than almost anywhere else on the planet. Parkfield sits directly on top of the San Andreas Fault. Geologists call it the earthquake capital of the world. They also call it a seismic pulsar. Because on this particular segment of the fault, something unnervingly regular happens. A magnitude 6. Zero earthquake has occurred here on a predictable 22-year cycle: 1857, 1881, 1922, 1934, 1966. The timing was so reliable that in the 1980s, the USGS famously forecast a quake here between 1988 and 1993. That one arrived late, in 2004. But the pattern held. A clockwork rupture, driven by the steady creep of the plates. The 2004 earthquake set the clock again. 22 years from 2004 is 2026. The window for the next Parkfield quake is not in the distant future. It is now. In March of 2024, a study led by Dr. Luca Malagnini, a director at Italy's National Institute of Geophysics and Volcanology, found that the fault was already showing the telltale signs of entering its final pre-rupture phase. His team wasn't looking at historical records. They were analyzing the seismic waves themselves, how they travel through the rock, how they decay, what is known as seismic wave attenuation. They discovered that the variance in that attenuation had shifted, signaling that the rock in the fault zone was critically stressed. The fault was hardening, getting ready to break. The study forecasted the main shock window to open in mid-2024. As of July 2026, that earthquake has not yet happened. Parkfield is late. The clockwork is broken. For seismologists, a predictable pattern failing is not a relief. It is a source of profound unease. It means the strain that should have been released is still accumulating. The segment is locked, loaded, and under more stress than the 22-year cycle would normally allow. The most predictable earthquake in the world has suddenly become unpredictable. The question was why? The answer would require an entirely new way of seeing the ground beneath our feet. For decades, seismology had a blind spot. It could only see the earth move when it shook violently enough to trigger an instrument. The entire science was based on detecting the sudden, brittle failure of rock. Movement that happened quietly, over hours or days, was effectively invisible. A ghost in the machine. It was assumed not to be happening. That assumption was a colossal error. On July 9, 2026, a paper was published in the journal Nature Communications that fundamentally altered our understanding of the San Andreas Fault. A team at the GF's Helmholtz Center in Germany, led by a postdoctoral researcher named Dr. Zara Zali, decided to apply machine learning AI to years of strain meter data from Parkfield. They weren't looking for earthquakes. They were looking for patterns the human eye had missed. The AI found them. It uncovered a hidden world of movement, what geologists call slow slip events. These are silent fault shifts, the San Andreas moving, but so slowly and gently that it generates no seismic waves, no shaking, no rattling that a traditional seismometer could ever detect. The fault was creeping, releasing tiny amounts of stress over hours, sometimes days, a process that was completely invisible to science until the AI learned to spot its faint signature. It was like discovering the planet had a second, silent pulse. But here is where it gets critical. Dr. Zali's team proved that these silent, slow slip events were not random. They systematically triggered swarms of low-frequency earthquakes, a known precursor to larger ruptures. The slow slips were priming the fault, pushing it closer to the edge. As Dr. Zali stated, faults can move in ways that do not generate strong seismic waves, and therefore escape traditional earthquake detection methods. Think about what that means. Scientists watching Parkfield, waiting for the big one, were only seeing half the story. The ground was moving beneath their feet, shifting, getting ready, and they had no way of knowing. It was a discovery as profound as finding a hidden current in a seemingly calm ocean. The very definition of a quiet fault was erased in an instant. The quiet was an illusion, and the implications were terrifying. If this was happening at Parkfield, the most densely instrumented fault segment on Earth, where else was it happening? The answer brings us back to the gate. The Cajon Pass is more than just a mountain pass. It is a geographic choke point for the entire state of California. Interstate 15, the primary artery between Los Angeles and Las Vegas, runs through it. So do freight rail lines and energy pipelines. It is a corridor of absolute necessity. Geologically, it is far more important. It is the complex, tangled knot where the massive San Andreas Fault and the nearly as powerful San Jacinto Fault run side by side, separated by only a few miles. This proximity creates the earthquake gate. The physics are brutally simple. An earthquake is a rupture that travels along a fault line, like a tear spreading through paper. When that rupture reaches a complex junction like Cajon Pass, one of two things can happen. The junction can act as a barrier, its complex geology absorbing and dissipating the energy, stopping the quake. Or, if the stress conditions are just right, the junction can act as a gateway. The rupture can jump across the gap, from the San Andreas to the San Jacinto, or vice versa. A multi-fault rupture. An event that doesn't just stick to one fault line, but triggers another, creating a chain reaction. The total length of the rupture grows, and with it, the magnitude of the earthquake. It is the ultimate nightmare scenario for Southern California. For years, the probability of the gate opening was just a theory, a debate among geologists. Then came the work of Dr. Lillian Burkhardt. Dr. Burkhardt, a geophysicist at the University of Bern, led a team that did something unprecedented. They didn't just model the next 100 years, they modeled the last 1,000, using paleoseismic data, rock samples, and advanced computer modeling. They reconstructed the history of stress accumulation at the Cajon Pass over an entire millennium. Their findings, published on June 3, 2026, were stark. Tectonic stress at the Cajon Pass is currently at the highest level it has been in the past 1,000 years. The modeled rate of what is called Coulomb stress, the specific shear and normal stress that pushes a fault toward failure, is accumulating at an accelerated rate just north of the pass. Dr. Burkhardt's conclusion was unambiguous. Our results show that stress levels on multiple fault segments are now at or above the highest values seen in the past millennium. She went further, stating that the region may be capable of a large through-going rupture involving both fault systems. 1,000 years of pressure. That is the force currently pushing on the gate. It is a number so large it's difficult to process. It predates the founding of most modern countries, a silent geologic inheritance of risk that has now come due. The San Andreas Fault south of the pass hasn't had a major rupture since the Fort Tejon earthquake in 1857. That is 169 years of strain building up. The Hayward Fault has been building strain since 1868. The Parkfield segment is stressed and overdue. And now we know the fault is moving in silent, hidden ways that were invisible until just months ago. Each of these is a single, isolated data point of extreme risk. But together, they paint a picture of a system that is not just stressed, but synchronized in its criticality. This is the new reality of California's earthquake risk. It is no longer about one fault. It's about how the faults connect. The discoveries of 2026 are not separate chapters in a story. They are paragraphs on the same page. Think of it. Dr. Pitarka's simulations show that when the Hayward Fault goes, the ground itself will become a weapon, amplifying the shaking by 50% in the most populated areas. Dr. Malagnini's work shows that Parkfield's reliable clock is broken, its fault segment now holding an unknown quantity of excess strain. Dr. Zali's AI research proves that the San Andreas is not quiet, that it is undergoing hidden movements which prime it for major failure. And finally, Dr. Burkhardt's 1,000-year model demonstrates that the one geologic gate that could contain a disaster is itself loaded to its highest stress point in recorded human history on this continent. This is not prediction. Prediction is a false promise. No one can tell you the day or the hour. This is something else. This is a condition report, a diagnostic on a system under impossible pressure. It is the geological equivalent of a doctor looking at a patient's charts and seeing every single vital sign in the red. Blood pressure, heart rate, temperature, all signaling a system on the verge of catastrophic failure. The common misconception is that California will one day fall into the ocean. It will not. It is a strike-slip fault. Los Angeles is sliding horizontally north toward San Francisco, but the civilization built on top of that sliding plate faces a more immediate, more tangible threat. Not a sinking continent, but a shaking one. Shaking in ways our models are only just beginning to grasp. The basin trap effect in the Bay Area is not a theory, it's a physics problem waiting for a trigger. The overdue status of the Hayward Fault is not an opinion, it is a mathematical calculation based on historical precedent. The 1,000-year stress peak at Cajon Pass is not a dramatic flourish. It is the conclusion of a peer-reviewed scientific paper based on a millennium of physical evidence. For the 8 million people living along the Hayward Fault, this research changes everything. An earthquake is no longer an abstract event. It is an event whose destructive power can now be quantified with 50% more accuracy and 50% more dread. For the millions more in Southern California, the integrity of the Cajon Pass is not an academic question. The difference between a contained magnitude 7.8 and a through-going rupture that jumps to the San Jacinto Fault is the difference between a disaster and a civilizational crisis. The science of the last few years has pulled back a curtain, but the view it has revealed is not reassuring. It shows us a world of quiet, hidden motion. It shows us basins that act as amplifiers. It shows us geologic gates strained to their breaking point over a timescale that dwarfs human history. Engineers can reinforce buildings. Governments can create emergency plans. But no one can stop the plates from moving. No one can relieve 1,000 years of stress. We are living in the quiet moment before the rupture. The uncomfortable reality is that thanks to this new science, we can now hear the silence with perfect clarity. And we know it cannot last. The pressure is still building. The gate is still holding. The question is,